the constant volume and constant pressure specific heat. In this section, we will consider a homogeneous phase of a substance of constant composition. Consider phase of a substance of constant composition. This phase may be a solid, liquid, or gas. But no change of phase will occur with no change of phase. We will then define a variable termed the specific heat. The amount of heat required per unit mass. To raise the temperature by 1 degree. Since it would be of interest to examine the relation between the specific heat and other thermodynamics variables, we note first that the heat transfer in the equation let me write the equation for the first row. And we have note that the heat transfer is given by the equation here. Plus dPe. Neglecting change in kinetic and potential energies. And assuming a simple compressible substance and a quasi-equilibrium process. We have this relation plus W, and we know delta W is P dV du plus P dV. We find this expression can be evaluated for two separate cases. Let me write again, delta Q equals to at 1, two problem special cases, constant volume for which the work term P dV is 0. So that the specific heat is can be obtained as so a specific heat at P constant which is equals to and for the second case, constant pressure for which the work term can be integrated and the resulting PV term as the initial and the final state can be associated with the internal energy term. A work term can be created and the resulting PV terms at the initial and final state can be associated with the internal energy term. As in section before, thereby leading to the conclusion that the heat transfer can be expressed in terms of the enthalpy change, the corresponding specific heat constant pressure Cp on P constant, H on T on P constant, and rho H on rho T on P constant. Note that in each of these special cases, the resulting expression contains only thermodynamics properties Cv at P constant and Cp on H on V on P on P constant, from which we conclude that the constant volume and constant pressure specific heat must be themselves be thermodynamic properties. So on because they expressed as thermodynamic properties, as we said before, it means that although we begin this discussion by considering the amount of heat transfer required to cause a unit temperature change and then proceed through a very specific development leading to this equation, the resulting ultimately expresses a relation among a set of thermodynamic properties and therefore constitutes a definition that is independent of the particular process leading to independent of particular property of a process leading to it. In the same sense that the definition of enthalpy in the previous section is independent of the process used to illustrate one situation in which the property is useful in thermodynamic analysis. As an example, consider the two identical fluid mass in this picture. At the first system, the 100 kJ of heat transferred to heat to it, and in the second one 100 kilojoule of work done on it. Thus the change of internal energy is the same for each, and therefore the final state and the final temperature are the same in each. So we have for the first one dE is 100, and for the second one dE also is minus 100, which is kilojoule. The change in internal energy is same. The state and the final temperature are same in each. So the final temperature dE1 equals to dE2. Final temperature is same. In accordance with the equation for the constant specific heat at constant volume, exactly the same value for the average constant value specific heat would be found for this situation for two processes, even though the two processes are very different as far as heat transfer is concerned. The special case for solid and liquid. In special case, consider either a solid or liquid, since both of these phases are nearly incompressible. So dH du plus dP du plus B dP. Also for both of these phases, the specific value is very small, such that this means the case is dH equals to du and equals to C dt, where C is neither the constant volume or constant pressure specific heat. Or constant pressure as the two would be nearly the same. In many processes involving a solid or liquid, we may further assume that the specific heat in this relation is constant, and the equation is unless the process occurs at low temperature or over a wide range of temperature. This equation can be written as H second minus H1 U second minus for liquid and solids. A specific heat for various solid and liquids are available in table A3 and A4. For liquids, for solids. F3. In other processes for which it is not possible to assume constant specificity, there may be a known relation for C as a function of temperature. C may be a function of temperature. The integral energy, enthalpy, and specific heat of an ideal gas is described in the next long section.